So in this video we're going to look at the intro material on vectors. Okay, so you'll find this material on our course page right here under intro material week 1. We've already looked at sets and subsets of R3, and so now we want to look at the section 1.2 on vectors. This section also corresponds with section 11.1 and 11.2 from our textbook, but adds some notation and terminology that I think to be important. So we're looking at the intro material on vectors. So you'll recall that we've already looked at the notion of a vector. So if P is a point and Q is a point, and these are given, right? Then we discussed the notion of a vector from P to Q. This is the vector from the point P to the point Q, right? And we discussed that as Q minus P, which means Q1 minus P1, Q2 minus P2, and Q3 minus P3. Okay. And we discussed that the picture for this is if P is some point and Q is some other point, that when you perform this operation right here, you get a new object that can be viewed as the vector from P to Q, which is just arrow. Okay, so if you were allowed to go in a straight line from this point P to this point Q, the vector P to Q would tell you how to go from the point P to the point Q in the straight line direction. Okay, so I guess we looked at some examples about that. So what we want to look at now from the notes, there was something that we can see here. Just what does it mean to be right here? What does it mean to just be the point with the vector symbol over it? So let's say I give you a point X over here. What is the meaning of just X with an arrow over it? Well, the meaning of that is that it's the vector from the origin to this point X, where O is what's called the standard origin, and this standard origin is just the point 0, 0, 0. Okay? So here is our standard origin, and the vector X is just this vector from the standard origin to the point X. So there is your vector X. So I guess a basic example here. Basic example is that if X is equal to the point 1, 2, 3, 1, 2, 3, then X is equal to the vector from the standard origin to X, which is otherwise known as X minus the standard origin, which is otherwise known, when you subtract those, you'll get 1, 2, 3. Okay? So there's your vector X. So in this case, often you'll have 1, 1, 2, 1, 2, 3. So here is your point X, and the vector from the origin to X, the vector which points from this origin to that point X, that's called X vector. Okay? So, you know, when we want this vector to start at the origin, that's what we call just the vector X symbol over a point. But we can see that we can define vectors that start at other points. So in this case, the vector P to Q starts at the point P and ends at the point Q. So it's important to just keep track of where this point of attachment is. So X vector has point of attachment given by the standard origin. But the vector P to Q, its point of attachment is the point P. Okay, so interesting. So let me draw another picture of that. So let's say that we have let's say we have these 2 points given, P Let's say we've got the point Q. We know that this is the vector P to Q. And we know that this is the vector P. And this is the vector Q. Okay. So our basic operations, basic vector operations that we have, basic vector operations plus, minus, and say scalar multiplication. Let's take a look at those now. You know, we've been kind of using this P plus the vector P plus, sorry. Yeah, if you want to add the vector P to the vector Q, you would just take the entries P1 plus P1 plus Q1, P2 plus Q2, and P3 plus Q3. You just add entry by entry. So this makes sense. Just from a, you know, a basic standpoint, that's how you would want to add these vectors. It also makes maybe algebraic sense, that's what I'm trying to say. And it also makes sense geometrically. So it's nice when the thing that you want to do also matches with what kind of actually also seems to make sense geometrically. So let's take a look at this. So let's take a look at the vector P, which is the same thing as the origin, the vector from the origin here to the point P. And let's take the vector P to Q, okay? And let's add those together. And if you add them according to origin to P plus the vector from P to Q, it kind of makes sense that if you want to add the vector P, so the origin to P, and then add on the vector P to Q, you're going to end up here, which also corresponds to the vector Q. So this should equal the vector Q, which is the same as the origin to Q. So take a look what we have here. We have the vector from O to P. We have the vector from P to Q. Since these insides match, the result should be this point and this point. So the vector from O to Q. This is O to Q. Okay. So let's double check that that makes sense with a number. So what we're saying here is that our algebraic sense hopefully will recover this geometric sense that when you add two vectors, you can either go the long way around, or you should be able to just point right there. But in either case, adding those two vectors is the same as going directly to this point. They should give you the same answer. Yeah, so if you take the vector Q to be take the point to be 1, 2, 3, and then the vector and the point P to be 2, 3, 4, then we know that the vector Q, which is the same as the origin to Q, that should be the same 1, 2, 3. The vector P, that should be the origin to P, which is going to be 2, 3, 4. Okay. Let's take this. The vector from P to Q, the vector from P to Q is do Q minus P. And the vector you get there is Q minus P. You'll get -1, -1, -1. Okay. So that is the vector from P to Q. Now let's take the vector P plus the vector P to Q. That's the same as the origin to the point P plus the vector from P to Q. Adding these together, entry by entry, which is what you'd want to do algebraically, 2, 3, 4, plus -1, -1, -1, and you will get 1, 2, 3, which is the same as the vector that's the origin to Q, otherwise known as Q. So that's just a quick example showing that your algebraic sense of adding of vectors makes sense also geometrically. So this is the vector-vector addition. Vector-vector addition. Subtraction works in the same way. One other operation that's going to be very important is, let's say that you do k times the vector q. So what was our vector q up here? It was 1, 2, 3. So you take any constant times the vector 1, 2, 3. That should be following just what you would want to do algebraically, k, 2k, and 3k. Okay. So for example, if k is equal to 2, 2 times q should be 2, 4, 6. Well, what did that do? This is what you'd want to do algebraically. Well, it has the effect of 1, 1, 2, 1, 2, 3. So here's your vector. Sorry if I can draw a straight line. Here's your vector q, the origin to the point 1, 2, 3. And then 2 times q has the effect of just lengthening. So here is 2q. So scalar multiplication just lengthens the vector by this number k. So that's it on your vector operations. I think you will compare what we have done in this video to the first couple pages of the vector section. The next video is going to discuss quite a bit more of this notion of a coordinate system.